About a month ago, I said I was going to put every other project in this room on hold until these two projects were executing code. This is a Bendix G15, a full-fledged vacuum tube computer from 1956, and it fully executed around 75,000 instructions. So, check. This is the UE1, a vacuum tube homebrew computer I've been building up for a couple of years, and it's not executing instructions, which means I have it's like December and I've got like 4 weeks to get this doing something really exciting. And we're close. This is a paper tape reader that I've been building from scratch for this. And as soon as this is working and inputting bits to this, it should start executing code. But this wasn't fully working in the previous episode. We had some interesting problems with it. So what I want to do today is I want to get this working at 100% and get this mounted right up here to this machine. But that's going to require making some modifications to this board and remaking this board, and we got just a whole lot of work to do, and I'll walk you through it as we go through it. So let's get started. So what is this and what is it that we're hopefully going to be plugging it into? Well, this is a optical paper tape reader for what I'm calling the UE1, a homebrew vacuum tube computer that I've been building from the ground up. And I based it very heavily on the Motorola MC14500, which is a 1-bit industrial control unit, but I didn't like the logic unit they had in it, so I swapped it out with a arithmetic logic unit so we can do addition and subtraction. But it is a true 1-bit machine. It only has a 1-bit data bus, so we're only working on a single bit at a time. It's also incredibly limited with RAM. We only have 8 bits of working memory. We have a byte of RAM. But the benefit is that our stored program can be arbitrarily long. We don't have the ability to jump back and forth within the program, but we can mask input and output. So if we build the program in a loop, we can effectively jump to different blocks by turning input and output off based on conditional tests of whatever values in the results register. But honestly, at the end of the day, it's a 1-bit processor with 8 bits of RAM. It's gonna be incredibly limited. And this was really just to kind of help me come to grips with how to do homebrew computing and how to do it with vacuum tubes. And I have a plan for something that is far, far better, with a full 8-bit data bus and ability to expand to a lot more RAM, and hopefully we're gonna get some core memory in there. But before I can get into any of that, I gotta wrap this project up. I can't leave this project unfinished because this is one of my favorite projects and I've been working on it for so long. So in order to wrap it up, we have to get this working. And the problem that we had with it in the previous episode was the paper tape loop was going around just fine, but I couldn't find the clock and the data didn't look quite right. And I think I've figured out what's going on. I've got the scope out here, and I've also taken the paper tape that we punched in the previous episode, and I've got it looped in here. And I think I've figured out what at least 2 of our problems are. It's important to note, though, before we get started, that the way that this paper tape is laid out is that you have bit 0, 1, 2, then you have the clock bit, then you have bit 3, 4, 5, 6, 7. So we have 3 bits, clock, 5 bits. Now, that's laid out on the exact same on my board back here. So I should be able to check in order from left to right, starting at bit 0, 1, 2, clock, 3, 4, 5, 6, 7, all the way down. So let's try that. If I go ahead and click the power on here, you can see our paper tape starts spinning around just fine. And if I check bit 0 here, this is our first major problem. You can see bit 0 is pretty much always at 0 volts. So maybe I've got that diode installed backwards. If I check bit 1 here, that's good news. We have data. That's excellent. If I check bit 2 here, we have our clock. That's a large problem. If I check what should be the clock, we can see that we actually have data coming on. And then if I continue on down the line, we've got data, data, more data, data, and then I get to bit 7, the very last bit, and you can see it's always high. So We have two main problems going on. Bit 0 is not functioning correctly, the clock is not in the right place, and bit 7 is always high. Now the clock not being in the right place and bit 7 being high is related because the V block that I built that holds the diodes in place is directional, and I'm like 95% certain I've got it installed upside down, which would shift all of the photodiodes down by 1. So that is our first problem. So I need to take this apart, get that V block off. While I've got it apart, I'm going to take a look at the topmost photodiode, which would be bit number 0. I think maybe I've got it installed backwards, and if I have it installed backwards, it's acting as just like a normal diode to ground, and that would cause it to always be low. All right, let's get this thing apart so we can fix my dumb mistake. With these two screws on the side removed, the V block pulls right away. The foam block behind the photodiodes is also directional, so I need to pull it out too. Thankfully, it just slides right out, easy peasy. And I'm going to use a punch to mark these so that I don't install them backwards again. And if we go back and look at the photodiodes, you can see that they are almost perfectly misaligned down 1 notch when compared to the photomask in front of them. What a silly mistake. Anyways, let's pull that data bit 0 photodiode out because something is definitely not right with it. A little solder wick and some gentle pulling got it right out, and hooking it up to my voltmeter here, it still seems to be working totally fine using the light on my phone. That's interesting. Well, I'm going to exchange it anyways, but I'll keep this photodiode for use in a future project. Once the new photodiode is in, I'll bolt it all back together, this time in the correct orientation. But if the photodiode was good, what else is there? The 100K resistor is pretty much all that's left, and checking from the 24 volt line to the photodiode should give 100,000 ohms. And on the other bits, this is actually totally the case, but on data bit 0, it's reading something like 1.6 mega ohms. That's definitely not right. Let's pull that resistor and give it a test. I've never had one of these resistors go bad, and checking it on the multimeter, yeah, it definitely isn't bad. That just leaves a bad solder joint, maybe? Looks like we might have lucked out. It was just a dodgy solder joint on bit 0, and they were misaligned. So let's kick the power on again. Our tape loop's going by. Let's see if we've got data. This is bit 0. That's data. Bit 1, bit 2, clock. That definitely looks like clock. Bit 3, 4, 5, 6, and 7. They are all wibble wobbling. So I want to build up the amplifier next, but that brings with it its own challenges. We have 8 data lines and a clock line all coming out of our photodiodes here, and they all look really good. They're wibble wobbling pretty much exactly like I would expect. Now we just need to increase their amplitude and square them off and send them out into the rest of the system. And that should be pretty easy to do. We just need an inverting amplifier and a cathode follower buffer. And thankfully, I had the foresight to build that. This board right here is exactly that. There are 8 inverting amplifiers on it and 8 cathode follower buffers on it. The only problem is that when we were looking at the individual data lines coming off of the photodiodes here, they all had slightly different shapes. And this is probably for 2 main reasons. One, the photodiodes are old and they're just going to be behaving differently from diode to diode, and that's not unexpected. And the other is that the light is going to be striking each photodiode slightly differently, and so that's going to change their bias up and down. And so when I built this, I didn't think about that at all, and it seems really obvious in hindsight, but everything seems obvious in hindsight. So when I built this, I made pretty much exactly this right here. So we've got our photodiode and our resistor divider network here. That's all on this board over here. And then we just have a standard inverting amplifier with a 220K, 220K voltage divider on it. And that's just flat out not gonna work. Each individual photodiode is going to need a custom bias. So I need potentiometers on each one, but I did not provide enough space in here to put potentiometers, and I really don't want to cut this board again. It is huge and it takes forever to cut, and this one actually works really well as it is. So I think we need to do a bit of a bodge. I'm going to remove all of the resistors here on the bottom. This is the voltage divider network, 220K, 220K with a 4.7K into the grid. I'm also going to remove all the little capacitors here. These are supposed to be desensitizing capacitors to prevent spurious impulses from going on, but I think speed is going to be more important than desensitizing the input. So I'm going to remove everything on the bottom side of these, and I'm going to replace it with this tiny little PCB that I've got here. This is my way of building bodges. I'm gonna put a 500,000 ohm potentiometer on here, and then we're gonna run some studs through it that then fall into the exact places of the pre-existing resistors, and everything solders in nice and tight. And I think it should clear the tubes and not look too atrocious. To get this modification done, first let's pull all 16 of these 6AU6s. Then I'll use my trusty Radio Shack desoldering iron and desolder all the resistors I need to remove. A small pair of needle nose pliers makes quick work of removing them. Rinse and repeat another 7 times. And this is why building computers is hard, not because of the design work, that's actually really fun, but because of how much repetition there is. At any rate, once I have all the resistors removed, it's time to start building up the little bodge PCBs. This is incredibly fiddly work, and my big dumb hands don't like doing stuff with this level of precision. I powered through it and check it out, 8 little daughter PCBs that should fix our adjustability problem. Now I just gotta solder these little guys into place. They all slot in just like they were supposed to, and with only 3 pins to solder per board, it was pretty quick work to get it all soldered in. And the result looks pretty dang good if I do say so myself. As far as bodges and hacks go, this one is pretty clean. Now we just gotta see if it works. But while we're doing time lapses, let's step out of the room and take a look at the mill. I need to machine up a new clock recovery board. Initially, I had planned to derive the clock from all the data bits ORed together, and that was a solid plan as it meant the data could come from anything. But since we have the actual clock bit on the paper tape, I'm going to try and use that instead. So a new clock recovery board needs to get cut. It's a really simple board, just an inverting amplifier and a cathode follower buffer. However, there are some extra provisions for a future expansion board that we'll get into in the next episode. Once all the soldering has been done, the two boards together look fantastic. This should contain 9 inverting amplifiers and 9 cathode follower buffers. So let's throw some electrons at these and see what happens. After a lot of soldering, I think we're at a position where we can actually test this thing now. I've got a makeshift harness coming from our phototape reader here that goes into the 8 inverting amplifiers here with the 8 cathode follower buffers, as well as a single line that comes over here to the clock recovery board. Now, I'm not expecting any of this to work initially because all of these potentiometers are going to be adjusted to whatever they were when they came out of the pack here. So we're going to need to plug it in, get it spinning around, and adjust each potentiometer individually. We're going to start with the clock here. All of the tubes should be warm, so all I got to do is plug this thing in. It should start going in circles. There we go. And actually, I can see a little bit of something on the scope already, so we may be pretty close. Oh, look at that. We're growing. There we go. Look at that. We've got a pretty nice clock going on. It looks like we're getting some strange long pulses here, and I'm guessing that's because of tape slippage, which is not super unexpected here. But if we change the time base down, that looks like a nice square pulse for the clock. So now we just got to figure out the tape slippage issue, but first I'm going to go through and adjust all of the rest of these potentiometers. I'm going to adjust it by just moving the oscilloscope probe right on down the line of connections here on the end, and then tweaking each potentiometer individually. It's actually really simple to adjust, and I should be able to adjust this on the fly for changes in ambient light, because so much of the photo reader here is open that ambient light could very well affect it. And with all of those now adjusted, this scope here has 4 channels. So let's get 3 data bits plus the clock bit all running at once here. I'll plug it back in and it should start singing along. Yep, there it goes. And the way I've got it set up is that the clock spans all 3 of our data bits, and you can see we have data and clock. Let's take a single shot of this. There we go. I'll turn that off so it's a little quieter in here. And if we zoom in a bit here, You can see that the purple trace and the blue trace look fantastic. They're going high before the clock pulse hits and going low after the clock pulse is done. But the green trace looks like it could use a little more tweaking. It goes high a little early and goes low a little early. That is interesting. And I bet you that that is due to a adjustment thing. I can probably get that green trace adjusted incorrectly. But seeing the blue and purple trace here do exactly what we're hoping they're do is just fantastic. I think it's time to finally start getting things mounted properly. We'll start with the primary inverter buffer board, and then I'll hold the clock recovery board up and cinch it down. The clock recovery board is smaller than the board it's replacing, but that's by design, and we'll see why in the future. With the two PCBs in place, let's hold the tape reader up and try to get an idea of where it's going to sit. Once I find a place I'm mostly happy with, it's time to get a lot of measurements so I can be sure that I put this thing dead square in the center. Next, I need to drill some holes in the aluminum base plate so I can mount it to the backboard. I just use a punch so my drill bits don't wander around, and I started with a small pilot hole and then upgraded to this larger bit, which works an absolute treat. I need to drill some pilot holes in the backing board as well, but so I don't make an absolute mess, I'm going to hold my vacuum nice and close to catch all of the wood dust. To mount it, I'm using large wood screws with spacers between the aluminum plate and the backing board, and I use the cordless drill to get the screws about 95% of the way in, but to make sure that everything tightens down correctly, I'm gonna do the last little bit here by hand. What a difference that made. It looks absolutely stunning mounted right here. I got so used to there just being nothing in this big empty void here that now that something's there, first of all, the whole thing looks a lot more complete, but also it just looks really, really cool. We're not fully out of the woods yet though, because it is mounted to the board, but it's not actually connected up to anything. Our temporary harness obviously isn't gonna work because I need to get the plug that's here connected up to here, here, and here, and that's gonna take a little bit of work. And instead of running some weird harness, I've actually got two more PCBs that I'm gonna cut. One of them is gonna sit right here, and that's gonna house all of the signals to get this into the rest of the system, as well as a relay that will allow us to halt the tape. So we can send a specific instruction that will cause the whole tape reader to shut off, and so we can run a program and then halt. And then I've got one more PCB I'm gonna build over here. This should have a single stepping feature on it. So we should have a bunch of toggle switches that we can toggle in an instruction with a memory address and then hit a push button to do a clock. Essentially like our remote control, but permanently mounted to the board. And then all that's left after that is to build harnesses. We have to build a harness that goes from this to this PCB. Then we have to build a harness that connects this entire thing to this entire thing and gets power into both of them. But we're getting close. Like the number of things left that we have to do, you can almost count on one hand. So it's getting pretty exciting, but it's running up to like Thursday afternoon, Thursday evening, and I really got to get this video in the queue to start editing. So I'm going to wrap this one up here, but we're going to be right back in this very spot next week. Hopefully getting both of those PCBs cut and getting most of our harness work done. So that way we can put some power into it and see how it doesn't execute instructions, see where we failed and get to work fixing on that. So I want to thank you so much for watching, and I hope to see you in the next episode.